Okay, good morning and welcome to MAE 113's lecture. Today we're going to do partial derivatives, and I think that's going to be some of the last material that, or well, that's the last material that we'll do of this course. Hurrah! We've covered a lot of material in this course, and we're going to do an exercise. We're going to go through partial derivatives, but before we begin, I have a couple of announcements. Some people were asking me what is going to happen with the exam. I can kind of give you a little bit more information now. So our final exam is going to be done in two parts. It's going to be done online, and we're going to have two parts. So the first part is multiple choice. So I haven't set how much time there is going to be on that. Maybe 30 minutes, maybe an hour. So that will be multiple choice questions. That's done through Moodle. That's you'll be clicking your answers on it, like you'll be presented a question, you'll have some choices that you pick, and then you just kind of click on the radio buttons, and you'll be able to work them out on paper if you'd like. You don't have to show any more work for that. You don't have to submit that. But there's a second part, which is the full solutions, and that will be where there's like a PDF that you'll have to download. You can print that off. You can write on that printout that you do, or if you don't have a printer, you'll be able to use like white paper or line paper, and you just write your solution. You can just read off the screen the answer, but make sure that you're like numbering the question, and then you write out your answer. And then so you write it on paper, and then you can scan it. If you have a scanner, you can photograph it using your camera phone. You can, if you have a tablet computer, you can write on the PDF and submit it. But basically, you have to get me your answers, whether they're handwritten or they're written on a tablet or whatever. You submit it as a PDF through Moodle. You can convert. The converting is your responsibility, partly because there's lots of other people who may have already done this before. There's lots of different apps. I'm not going to specify which apps you have to use. I don't, because everyone's got different equipment, and they're all, or people are all used to different things. But basically, just you have to get me to a PDF. If you've never done that before, there's apps like Dropbox where you can actually scan the document with a camera phone, and it just takes a couple of seconds for the page, and then you will click on like a plus, and you can add a page, scan the next page, and eventually you'll have a PDF, and from that it's in your Dropbox. You just submit that, or you go to your desktop or your laptop or whatever, and you drag that file into Moodle and submit that for your final exam. Then I recommend you use a black bold pen so it scans well. I'm using black pen all the time when I'm teaching here, so it shows up on camera. If I can't read it, I can't give you marks. If it's kind of, I find if you're using pencil, in general, it doesn't scan very well. They have gotten better over the years, but again, I would say test your setup first. Don't come into the exam, write it all in pencil, and then realize, oh, I can't submit this. It's not scanning well. You're going to lose marks. Don't do that. Be prepared. Test out what you're going to do. Okay? Yeah. What else are we going to cover about the exam? I think that's it. Without and we'll talk more about that next Thursday, next Thursday. I plan to have a final quiz, and I'll send out an email again to just kind of warn people that we're going to have a quiz next Thursday. But the goal of the quiz is Partly to test some of the material that we've covered in the last couple of 2 or 3 weeks on YouTube here, but also to, so we're covering material, so that's part of the goal, is to see whether or not you've been keeping up. The other part is to basically, as a dry run. So, I'm not sure which kind of a style of quiz yet we'll do, but something along the lines of maybe like we'll do the multiple choice, and you'll be able to see like, oh, you can just click on the questions and then submit them. Or we could do something where like I just post the page online, you download it, you write out your solution, and then you scan it and submit it. But I just would like to go through something like that on a quiz or something like that where it's not really worth a lot of marks, and so that we don't want to pile on the stress of also doing, and that you're doing an exam and this is a lot of material. I don't want to pile on the additional stress of, oh, and yes, and technology isn't working. So we're going to do a dry run next Thursday. What else? Where some people are celebrating Ramadan, some people are celebrating Passover, and tomorrow is Good Friday, and I'll be celebrating Easter over the weekend, so also Easter Monday. So Friday and Monday, there's no lectures. But to make up for some of this, because we've covered all the material in this course, but what I'll do is on next Tuesday, I'll do something from like 7 p.m. to 9 p.m. Eastern Standard Time. We'll do a tutorial. These are always scary for me because this is where you come with all the questions, and hopefully I have the textbook and I remember everything, and I do this live, and hopefully I don't make any mistakes while I'm doing it. So that's what we'll do for Tuesday, just to make sure that I've covered. I give you what you're paying for. You get your 2 hours, and because we got shoved forward into April and into the holidays, I think it's fair that we do some 2 hours of prep for the exam, and so this is kind of like for your exam. Okay, enough of me blabbing. Blah 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 blah. Announcements. So we've done all that. We want to get on to the fun stuff. This is page 2. Okay, so let's do a quick exercise this morning. This one comes from section 6.5. This is question 23. And what we're going to do is the integral from 1 to 2 of x squared plus 2x all over x cubed plus 3x squared minus 1 dx. Okay, so for the couple of people that are watching right now, take a moment and do this. Just, pull out some paper, like take out some scrap paper and take out a pen and just write it out. And just take a moment. If you get stuck, the hint is we're going to be doing this by substitution, so try that. I'll give you 2 minutes and then I'll be right back. Okay, so hopefully you have this. Well, I have coffee. Let's do this. All right. We're going to do a substitution, and we're always looking for something that when we take the derivative of it will help to eliminate kind of like this dx here. So if I know I need to take a derivative, it means I'm going to be dropping down a degree. I can see already there's an x cubed, and I have an x squared up top here. So more than likely what I'm going to do is I'm going to take this part down here, and that's what's going to become my u. So let u equal x cubed plus 3x squared minus 1. If I differentiate that, I get 3x squared plus 6x, and the minus 1 is 0. Okay, definitely not what I have up here, but I notice that everything is multiplied by 3 here. So what I can do is factor that out. So I get the 3, and the 3 comes out, and we're going to factor that out. So I get x squared plus 2x. And I still have my dx here. Okay, and then I can bring that 3 over to the right hand side, so I get 1/3 du is equal to x squared plus 2x times dx. And so that's what I have right here. Okay, so and what we're doing again, because this is a definite integral, what I have to do is I'm going to solve the indefinite first. And what I'm going to do is I'm going to split this fraction up just to illustrate this a little better. Okay, so this part is equal to 1/3 du. And this part right here, that's equal to 1 over u. So that means that I need to do the integral of 1 over u times 1/3 times du. I can bring that 1/3 out in front. And I know, yes, you do have to factor out the 3. Good. Okay. Yes. Okay, good. And, okay. When I integrate 1 over u, that becomes ln the absolute value of u plus a constant. So then when I actually do the definite version of it, I have to substitute, I have to make sure I substitute back in what my u was, so it's 1/3 ln x cubed plus 3x squared minus 1 plus a constant. So in this case I have it's 1/3 ln of x cubed plus 3x squared minus 1, and we're going to evaluate that from 1 to 2. Good. And then we shove in our limits. We have it for 2. We have to evaluate this for 2, and then we subtract this evaluation at 1. So it's all this crap at 2 minus all this crap at 1. So plug this in. Okay, so I have, this is 8, so 2 cubed is 8. I have 2 squared, that's 4 times 3 is, 4 times 3 is 12. I need more coffee. Let's go. 1 plus 3 minus 1, so those ones cancel, so I'm just left with 1/3 ln of 8 plus 12, that's 20 minus 1, so it's 19, minus 1/3 ln of 3. I'll factor out that 1/3 so that I'm left with ln of 19 minus ln of 3. And that's the answer for that. You don't have to worry about, well, okay, so when I take the absolute value of 19, it's still 19 because it's not negative. So I don't have to worry about that. And I'm done. So that's what's in the back of the book. I think when I finally wrote it out, I think I did something like that. But, you know, it's the same thing. Doesn't matter. Good. Hopefully that's the answer that you got for that. If you didn't, probably drink more coffee. That always helps. And try a different problem out of that same section. Try probably section 6.5, 24. Probably it's a similar question. Ooh, okay. Number 3. Okay, so now we're going to move into probably stuff some people have never seen before. This is functions of 2 variables. And basically, you know, a function of 2 variables consists of this is you know, a set of x and y points, so this is what we'll call the domain, and it gets mapped to, you know, some value z, or just like that. Why do we use something like this? In one variable, we have, say, a cost function, and we'll say like x, and say x is the number of units. This is our cost function. And x could be the number of units that are made, is the number of units manufactured. That's in one variable, but we can also say, could have a cost function that's, say, not of just x, but of y. And this is where we have 2 independent variables, meaning something along the lines of, if I had a cost function, this is x is the number of units of a particular model, say model A is manufactured, and y is the number of units of model B is manufactured. And so you can have functions that have 2 variables. Now you have to plug in 2 numbers and calculate it. So let's do, you know, let's move let's give like a little example of a function that is got two variables. So here's a function f of x and y, and let's say that this is x plus 2xy plus y squared plus 3. Now, if I was told, like, okay, tell me what the value of this function is at the point 0, 0, well, all you do is you replace the values in here. This would be for x, and this would be for y. So substituting those values in, I would be 0 for x, so 0 plus 2 times 0 times 0 for the y. So this is my x, here's my y, so I'm just gonna, here's my x, 2xy plus, inside here is my 0 as well, so there's my y squared plus 3. This is 0, this is 0, this is 0, plus 3. So my function at the point 0, 0 is 3. If I did a different point, let's say f of 1, 2, so this is the point, like the function at the point 1, 2, same idea. I have to replace, this is my x, and this is my y. So there's x, so I need to put in 1 plus 2, and my value for x in this case is 1 times my value for y is 2 plus my value for y squared is 2 squared plus 3. And then I just calculate that. So I have 1 plus 2 times 2 is 4 plus 4 plus 3 gives me 9 plus 3 gives me 12. Now, oftentimes you'll find that, you know, there are computer packages that graph these types of functions. Yeah, let's try. Let me show you. We can actually do it even by hand. Sometimes, if you work with stuff long enough, you start to recognize what the function looks like without even having to graph it. But again, this is what I will call intuition, or just basically experience over time. If you're working with cost functions of a particular type all the time, you'll kind of know what they look like. If you start to work with other types of functions where we use it in probability, you'll start to see them. But let's start off with a common or an easy one we can do. Let's do an example. And I'll say, let's look at this function x, f of x, y. And this is equal to x squared plus y squared. And what we do is we kind of create what are called level curves. And eventually we'll create what's called also a contour map. But what I'll do is I'm going to pick some values for what f of x, y is going to be. So if I did f at x, y is equal to 0, that means that x squared plus y squared equals 0, and that the only solution for that is when x and y is equal to 0, 0, which means that this is a point. If I did f at x, y is equal to 1. Then this is x squared plus y squared equals 1. And this is a circle then with radius 1. And already you can see what I'm going to do next. If I picked 2 squared or 4, that's equal to x squared plus y squared equals 4. Or this is a circle with radius 2. So if I just drew in, what I'm going to do is draw these curves, or these level curves. So what I have is here's y and here's x. If I start at 0, that's just a point. So that is when f at x equals 0. The next point that I could do is, here's 1, we'll do there. This is where f at x, y is equal to 1. I can do it for 2. I'm trying my best to draw concentric circles here, but that's equal to 4. And so what that is doing is it's helping us to kind of visualize. If I start at 0, like on the level here, it's at a point, and I'm kind of doing these cross sections through it, so that if I draw this in 3 dimensions, so now I'm going from, this is my x, and this is my y, so this is taking this plane and it's down there, and I have my z direction here. If I start out here, there's the point there, my 0. At the next point here, which would be, say, 1, that's where the value is. I have a circle here that's centered at this, and my radius is 1. And the next one that I have is at 4, so I have 1, 2, 3, roughly 4 here, and I can draw another one, and it's going to have a radius of 2. And so what this function is kind of looking like is like this. So in 3 dimensions, you kind of get that. It kind of looks like a, well, the parabola. Well, it's going to be a parabola any way that you start to cut it. And yeah, so it's kind of got this bowl with a very with a point on the end of it. And we see stuff like this all the time. We see this in things called like topographical maps, where we actually have cross sections. So just kind of give you an idea, this is from my old text, not my, like I didn't write this book, this is my professors from 10 years ago, but here's an example. Hopefully it's in focus. So again, there's a mountain, and what we do is we take cross sections of it, we slice through it, and we project it back down onto a map here. So, and we start to put little numbers on it, say here's sea level, and we can kind of project to it, and we just kind of do these slices through it. And usually what you start to do in, say, like topographical maps, these are called contours, and you would put little numbers, and you would look to see that these numbers are increasing or decreasing, and so you can kind of build those images up into your head. For instance, you would do those slices, and you would build this image back up in your head. I was looking for, it's previously, of course. So again, here's a contour map of the Himalayas, and very small numbers right here. You start to look where the lines are, and you can see that here is 6788. You follow those lines. Oh. There's like 64. But as you can see, some of these are numbered, and what you'll find is that if you're going towards certain lines, you're going up a hill, or if you're going away from certain lines, you're going down a hill. And again, we can have different kinds of graphs here, and I was just trying to see if we had the other one that I knew about was we also have something like isobars, but I think that's in the other textbook that we have from Sutan. He gives a great, sorry, I didn't mean to knock the microphone. He gives a great little example of it where, and I'm going to show you in the textbook because there's some students who weren't able to take the textbook home with them. So that's because of weight restrictions due to airlines or whatever. So hold tight just a second. I had it. Oh yes, this is also perfect too. So there's like an example of a topographical map. You have a contour for the mountain peak, and you can see here are the contour lines. And we have 400, 800, 1200, 2000, 1600. So you know that if I took, I wish I could draw on this. Okay, I'll try not to. If I took a path up this way, I know that I'm increasing up this hill. And if I was, say, if I picked a different path, say here, I know if I was walking this way from 1200 to 800, I knew that I would be going down a slope. And so I can kind of build these slices up in my head. They're getting higher and higher. And so I kind of mentally build this image in my head. And this is where I had seen this. Here's what they call isotherms. These are curves connecting of the same temperature. So right here we have 30, I have 40 here, I have 50. Oh, this makes sense, of course, as we're going further south or towards the equator, we're going to get a little bit warmer. So here this is just an outline of the United States. So this is where the Great Lakes should be, and we're right about here. This is in Fahrenheit. I wish we were having 30-degree weather. So we're about here, but as we drive down south towards Florida, we're going from 30 Fahrenheit to 40 to 50 to 60 to 70. So if I kind of took my path here, I would see what that I'll be increasing in temperature. And if I started out like in California and drove this way, again, I would be going from 70 and crossing to 60, 50. And again, I would assume that there's like a gradient of, there's a kind of a some sort of change. I don't necessarily know, but again, this kind of gives me a rough idea that as I'm following a certain path through this map, I'm decreasing. Okay. So you can already see where we're going to go with this. If you can see changes in something in terms of either elevation or slope, then of course we're going to apply a derivative to it. Now, because we're using functions of two variables, we use something a little different. There's a little tweak on what we use for derivatives. Okay. So lots of cool examples that we use. We use these. I'm sure the military has trained people to use a topo map, and that's what it is. So that you can see elevations and stuff like that. Also, it works for temperatures. We see it in weather reports. So again, now that we see that there's changes as x and y vary, we'll want to look at the derivative or the rates of change. So we have partial derivatives then. In our definition of the derivative for a single variable is that we're looking at the change in the slope as the distance between the 2 points get really, really small. So again, that's the function at x plus a small change minus the original function all over delta x, which is our run. So we have our slope, we have our points, so we have our 2 points here, and we let that delta x get really small, so that these 2 points get really close but don't touch, and that's our derivative. Okay. So what do we do when we have two variables? Well, what we do then is we'll look at the change in one direction or in one variable. So for instance, if I wanted to look, I have my function, let's say if I wanted to look at the change in the x direction, the y direction is fixed or constant, then what we do is we have f at x plus a small change, comma y, minus the original function all over the small change in x. So we'll let that delta x get really small, and that's it. This is what we call the partial derivative and this is with respect to x. And we use a different notation in this case. So this is my function, and we use what's called die, basically. It's a little kind of curly d, So we use a curly D or die f by die x, and that tells me it's the partial derivative of f with respect to x. So if we wanted to look at, okay, that's fine for the x direction, can we also do the same thing with the y? Answer is yes. Which means, so there's the change in the y direction, and that means that the x direction is constant. And instead of die f by die x, we're using die y. So, and the same idea applies. We're going to do f at, so we're not looking at x in this case, but we're going to vary the y. So we do f at x, y plus delta y. So we're changing not just we're not doing a delta x anymore, we're doing a delta y. Minus the original function all over delta y. And so the limit as delta y goes to 0 gives me then the partial derivative of f with respect to y. Okay. That's the definition of the derivative for a partial derivative. Okay. So we were able to do this for one derivative, or for one variable. We can also do this for two variables. You can also do it for three variables, but let's just keep it straightforward with just two variables at the moment. And let's do an example. So this is page 4. So let's do the derivative of this. Partial derivatives of f at x. Y is equal to x squared plus y squared. We've already kind of drawn it. So if I, fix a y and I just kind of vary across the x direction here, because of the way that because of the function, it's very symmetric. So I would expect that my slope as I'm going across or going up is going to be increasing, and it would be increasing at the same rate as in the y direction. Okay, but let's do this. It's actually not, I know this might look scary, but it's really not. It's the same thing that we've done before in terms of doing a derivative. We just kind of switch the notation a little bit using a curly D. So if I have f at x, y is equal to x squared plus y squared, what I need to do is, let's say I want to find what the partial derivative of f with respect to x is equal to. So in this case, I just need to take the derivative with respect to x. And the same thing applies. This is a sum rule. So I can do the partial derivative of x squared plus the partial derivative of x of y squared. So I just take the derivative of this with respect to x. So of x squared, that just equals 2x plus. Now I have the derivative with respect to x of y squared, but there's no x here. So there's no variable, and basically I treat this like a constant at this point because there's no variable of interest. I can't differentiate that. Well, I can differentiate it. It's just 0 at this case because there's no x. So that would almost be very similar to if I took the derivative of dx of, say, the number 9, that's equal to 0. Again, there's no variable there for me to differentiate. So I treat it like a constant, and I take the derivative of a constant, that's equal to 0. There's no change because it's constant. If I take the partial derivative with respect to y, I can do the same thing again. I have my sum rule again. I can just apply the derivative to each individual term here. Now, when I take the derivative with respect to y, there's no y here. So this ends up being treated like a constant. And because it's a constant, when I take the derivative of that, that's 0. Now I have the derivative with respect to y. If I take the of y squared, the derivative of that is 2y. So we found the partial derivatives with respect to x and the partial derivative with respect to y, and that's it. So you could get questions like this. What is the rate of change of the function f in the x direction at the point 1, 2. Okay, so that means it's the partial derivative in the x direction, so that means the partial derivative of x at the point 1, 2. And we've got that derivative, so that's 2. And we got to substitute in 1. So it's just equal to 2. So that is f increases 2 units for each increase in the x direction with y being kept constant. In that case, y is equal to 2. And the same thing, what is the rate of change of, I can write it again, but what is the rate of change? I think you can already guess we're going to go with this in the y direction. So rate of change of the function f in the y direction at that particular point, 1, 2. Okay, and in that case, our partial derivative is 2y, so it's 2 times y, and the y value in this case is 2. So that's equal to 4. I won't write this. Okay. Sure, I'll write it out. So that is f increases 4 units for each increase in the y direction, with x being constant. So why am I showing some of this is because then I get to also review some of the rules for differentiation, of course. So let's do 5. So let's do another example of just doing partial derivative, but what I want to do first is let's do this function f of x, and let's do (9x over x squared plus 9 squared), which means that we're going to have to use the quotient rule. Remember, if we have the quotient rule, if I have the derivative with respect to x of f over g, it's the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function all over the bottom function squared. So if I differentiate this, I take the derivative of the top function. So let's see. There's my f prime. So I need to take the derivative of the top function. So this is this. So it's just 9. Use purple. Then I need to do the bottom function. So times x squared plus 9 squared minus, I need the top function again, but I just leave it alone. So that's 9x times the derivative of the bottom function. Ooh, that's not a good color. Bottom derivative. So I have times 2x plus a constant, so that is done. All over the bottom function squared. I can factor out that 9 so that I'm left with 9 times x squared plus 9 squared minus 2x squared just simplifying this, I have say 9 squared minus the x squared all over the denominator squared. Okay, and I'll leave it like this. But you're probably going like, Richard, why? Why are you doing that? Because it's similar. It's a similar problem to what it's going to be a similar problem for what we're going to do next. Okay. If I do that, ooh, nice. Okay. Call this 6. So, if I did this function here, f at x comma y is equal to x times y all over x squared plus y squared. And then I wanted to find what the derivative, the partial derivative is with respect to x. That means I need to take the partial derivative with respect to x of that function. And in this case, again, that means I just have to apply the quotient rule to this. But just think of it as that y being a constant, just like here, which is a 9. If I have to take the derivative of this. So if I'm taking the derivative of this, it means that I'm going to have to take the quotient rule. So it means I still apply this same idea to the partial derivative. But again, I'm just taking it with respect to x. So it's the top function, so I got to take the derivative of this top function with respect to x times the bottom function plus, I leave the top function alone for the second part here, times the derivative of the bottom function take all that, and the denominator is squared. Okay, so now when I take I've applied this as the quotient rule. So then the next thing I need to do is take the partial derivative. Okay, so I have x times y. The y is treated like a constant, and I'm just having to think of it as like 9, just like 9x. So if I treat the y like 9, then when I take the derivative of that, it's just 9. So that means that in this case, if I take the derivative of this, I'm just left with y. So it's y times x squared plus y squared plus x times y, and now I need to take the derivative with respect to x for this, x squared plus y squared. The derivative of x squared is just 2x, and the derivative of y squared with respect to x is just 0, because there's no x, so you treat that like a constant. And so I'm just left with, so there's plus 0, so I just leave that. And then it's the denominator squared. And we can clean this up just a little bit. I will pull out that y. So I factor out that y. So at this point I'm done my differentiation. I'm just cleaning it up. I have x squared plus y squared plus 2x squared all over x squared plus y squared. And almost done. X squared minus plus. Oops. Should be a minus here. Yes, thank you. Yes, 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 yes. Good. As I was saying it, I was like, it should be a minus. So x squared minus 2x squared, so that should be, so I'm just left with y squared minus x squared all over x squared plus y squared equals 2. Okay, so very similar. I just replace this y with a 9. So I had 9x over x squared plus 9 squared. So here it is like that. And very similar answer again. So I have the y is equal to 9 in this case here. So I have 9 times 9 squared minus x squared all over x squared plus y squared all squared. Okay. So we can do the same thing again with respect to y. Let's see where. Okay, am I still within the screen? Okay. So if we're going to take the partial derivative with respect to y, that becomes just like that. Move that away. So same idea again. We have to use the quotient rule for this. So instead of treating y as a constant, when we're taking it with respect to, when we're taking the partial derivative with respect to y, we have to treat x as the constant. Okay, so again, we can do our quotient rule, which tells us it's the derivative of the top function times the bottom function minus the partial derivative. Well, we got to take the derivative of the top, or we take the top function, multiply it by the derivative of the bottom function. And we divide it all by the bottom function squared. So taking the partial derivative with respect to y, again, the x becomes like a constant at this point, so you can think of it like 9y. So what's the derivative of 9y? Would be just 9. In this case, then, taking the derivative of that leaves me with just x. So you can even think of like, so think of x as a constant. You can even think of it like x equals 3, so that when you're taking the derivative of that with respect to y, it's just like 3y. Well, what's the derivative of that? Well, that's just equal to 3. So in this case, I'm treating the x like a constant. If I take the derivative with respect to y, I'm just left with x. And now I need to take the derivative with respect to y of x squared plus y squared. So this is equal to 2x. Oh, no it's not, because I'm taking it with respect to y. And there's no y here. So I treat that like a constant, and the derivative of a constant is 0, so it's 0 plus the partial derivative with respect to y of y squared is just 2y. And I can clean this up just a little bit. I'm just going to 2xy squared all over x squared plus y squared all squared. And I think I can factor out that x up top here so that I'm left with x squared plus y squared minus 2y squared and almost done. Y squared minus 2y squared gives me minus y squared all over x squared plus y squared all squared. So you notice it's very similar. In this case, what we've done is basically exchange the x and the y at this point. But there's our partial derivatives of it. So what's the next part? So in one variable, functions, I have, say, f at x, or just say y, and my derivative of that would be, say, y, or sorry, f at x, or sorry, f prime at x. Or I could also have dy by dx. I could have the second derivative of well, or that's equal to dy squared over dx squared, and so on and so forth. When I move to two variables, I can take a derivative in either the x or the y. So if I have an f, say I start with a function, I can actually go and take the partial derivative in the x direction or in the y direction. And that gives me the partial derivative of f with respect to x, if I take it with respect to x here, or dy f by dy y, if I take the partial derivative with respect to y. And if I take the second order, or the second derivative, the second partial derivatives, again, I can take it with respect to x or with respect to y. So I can have here again, here's die x. So I'm taking the partial derivative with respect to x. So again, I can have die f over die x squared. I can have die by die y of die f by die x, and that gives me die squared of f over die y by die x. So in this case, I have die f by die y, and I then take the partial derivative with respect to x. So that gives me die squared of f of die x over die y. So in one variable, if I take the second order derivative, I have, just one, because I'm only working one direction. If I have two variables and I take the partial derivatives with respect to one direction and then another direction, there's 4 different partial derivatives that I have of the second order. And if you remember, you're counting from 106, that this is going to be moving in powers of 2. So I have to the 1 here, so there's 2 directions or 2 choices that I have here, so there's 2. I'm moving to the next one, so this is the second order partial derivative, so that's 2 to the 2, which gives me 4. If I went to the third partial order, that would be 2 to the 3, so there would be 8, and that tree grows on. So we can actually take partial derivatives again with respect to either variable x or y. So also I'd like to point out, in general, these are not equal to one another. Okay. So let's go back to an easier one. Going back to this. And this is page 8, but I'm continuing from this example here. There we go. If I wanted to take the second order derivative, that requires me to take the partial derivative of df by dx, and I've already calculated what that is. So that's equal to 2x. And if I take the partial derivative of that with respect to x, because there's only just x there, derivative of 2x is just 2. So that's done. If I wanted to take the the second order partial derivative of f with respect to y that would be the partial with respect to x of di f by di y. And in this case, it's 2y. So again, taking the derivative with respect to y, I'm left with 2. If I wanted to take the di squared f by di y by di x, I would need to take the partial derivative of y with respect to of di f by di x, which means me substituting that in is 2x, and in this case I need to take the derivative of 2x with respect to y, and there's no y, so this is treated like a constant, so that is equal to 0. And similarly again, I want to do the di squared f by di x by di y, I need to take the partial derivative with respect to x of di f by di y. And if I substitute that in, it's just 2y. So now I need to take the partial derivative, or the derivative with respect to x of 2y. There's no x, so that's equal to 0 too. I do want to point out, even though that these were equal to one another, in general, changing the order, like di y by di x and di x by di y, does not make those functions equal. So just be careful. I know they both ended up in 0 and that they're equal to one another, but that's in general, it doesn't hold. Okay. And that kind of concludes the material that I'm going to teach for this course. Why did I make you guys go through the partial derivatives? Because it's used later in higher up courses. Unfortunately, I wish I was there. I could teach more of this. It requires a little bit more time and a little bit more finessing. But in our textbooks, why are we looking at partial derivatives is when we get into multivariable functions, we're using f of x and y's. Again, we have these kind of 3D objects or 3D kind of graphs, and again, the same questions we apply in optimization is like where are the global maximums, where are the global minimums, where are the locals, and so forth, because these functions are describing something like cost, and we want to minimize cost, or there's something like they're describing our profit and we'd like to maximize it. So in sort of like this could be a great function that describes our profit, and we want to find out what the variables x and y are so that we can maximize our profit. Or we could have a function like this, which is like our cost functions, and we can have a cost function in 2 variables, and we want to find out what the minimum is. It just works in this case because we are working with a formula that is a circle where we normally wouldn't be working with circles. I don't know about in economics, not necessarily. You can get some weirder looking functions in general. You can get functions looking like this, and in this case actually we have a minimum in one direction but actually a maximum in a different direction. So in this case I have a y and here's an x. In the y direction actually I have a minimum, and in my x direction I've sliced through here, that's actually a maximum. So like you can actually get some things that are called like saddle points. And because we got like two different cases, we got like minimums and maximums, and now we have these kind of weird things like saddle points. We have kind of a more, the complexity of solving the problems increases. And so we can get into stuff like this, which is determining the relative maxima. And so in this case, we're taking the partial derivatives. So in this case, this would be di f by di x. And in this case, this would be di f by di y. Again, we find the derivatives, in this case the partial derivatives, we set them equal to 0. But now I have two functions, means that I need to solve for those systems of equations now. Makes it a little more difficult. And then the second one is we have to do a second derivative test, so it means you have to take the second order partial derivatives, and you get kind of a test. You'll get a number, and with that number you follow through the procedures to find whether it's a maximum, a minimum. There's one where it's neither, or you can also come up where it's inconclusive. Yes, when you said that in the case of the examples we just had, that second partial, they did equal to one another. Yes. You'll find in applications that they do equal one another, but don't think that in general, like all functions, if I take the partial derivatives, if I change the order, that you're going to get the same thing. Most of the time it works okay, but don't generalize that to the full general case. So again, that's working in two variables here. Again, you can start to classify then the extrema that you find. And again, here's something very similar. There's somebody who's got a profit function x and y. Here's your revenue function minus your cost. They have to solve an equation to find a point, and then they have to test it. So this is not what's being covered on the final exam, but this is stuff that will be needed eventually in higher up courses. They'll have to walk you through this. And then you'll get to people who will use method of least squares. No, and that's not what I was thinking of. There's another one called Lagrange multipliers. And again, this is constraining it, but there's some people in the class that don't need this, and there's some people that will have already seen this. But in each of these kind of higher up cases, they all require you to be able to differentiate or to find the partial derivatives. And these are it. Yes. Okay. Perfect. So is there any other questions concerning about partial derivatives? what's kind of nice is that all you have to do is just, whenever you're taking the partial derivative with respect to one variable, you have to make the other variable, like, treat it like a constant. And once you do that, everything else remains like the same as when we're working with one variable calculus. So if I was taking the derivative of this, remember when I was working with ln of x, let's say x squared here, there's a couple of ways I could do this. I mean, the first way is I could bring that 2 down, and then taking the derivative of that gives me 2 times 1 over x, or 2 over x. The other way that we could do that is using the chain rule. So again, it's 1 over x squared. So it's 1 over what's inside here times the derivative of the inside function, which is 2x. And I have 2x over x squared, which means that I can cancel out one of those x's, so I'm just left with 2 over x. So again, 2 different ways of doing the same thing. But the same thing applies here. If I took the derivative of f with respect to x, it's again 1 over what's inside of the function, and then I need to take the derivative of the inside function. So that is just applying this now to this. I have the derivative of x squared, which just gives me 2x plus 0. So I'm just left with 2x over x squared plus y squared. Okay, so is there any other questions before we break for the holiday? Okay, if not, you know where to reach me. You can reach me through my email address at rmc.ca. Yeah, and I usually have my phone or my computer is dinging to remind me that people are emailing me. So yes, I'll answer you as soon as I hear it or I'm aware of it. Yeah, don't hesitate to send me an email. We covered all the stuff about the exam. We have, if you have, and again, we'll meet again on Tuesday. I'll send out an email about like 30 minutes before again, and people can join and ask questions. And I'll have, what is the quiz on Thursday covering? That's a good question. Well, the quiz on Thursday, we should, we did, well, we did indefinite integrals. So you should be able to, we did all those integrations. So you should be able to do something I don't know, hopefully x squared dx, or something like x to the minus fourth dx, or, integral of 9x minus 3 plus 10x, something like that. There's also definite integrals that we did. So we could, something like that. There's definite integrals. What else did we? We also did some applications. But that was just more for illustrative purposes. We also did the substitution rule. We spent a lot of time on that, so hint, probably something on this. We did an exercise this morning already, so partial derivatives. So the quiz will probably cover something like that. You'll probably have like 20 minutes, 20, 30 minutes. I don't know. We'll see. Again, we have to set it all up through Moodle. And if you're asking about assignment questions, we did lots of stuff in the lectures and stuff like that. I would look at questions like that. I would also say pick questions out of the relevant sections and work on those. We've done lots of them in the lectures, so, or the tutorials, so go through those if you get stuck. But again, pick a question, work on it, check the back of the book. Check the I would pick odd numbered exercises. They have the answers at the back. If you get stuck, send me an email. I'll write you out a solution, or send me what you have. I can look at it and be like, oh no, this is wrong, or this is right, or I don't know what you're doing there. So that's what we're I wish I was able to see you face to face, then I could tell you what you're screwing up, but that's such as life. Welcome to the online world. So we'll have to do it by email, and you know what it is, send it to me. We can chat back and forth that way. And with the consideration of PDF scanning, is there some allowance for time beyond the exam for scanning time? Again, that's a good question again. What I've heard my department head utter is they'll usually say, like, here's 3 hours of time, and then they let you have like 10 or 15 minutes at the end to get your stuff together and ready for submission. I don't know. I don't want to say that yet. Again, these are kind of like what people are saying. I don't know what the registrar is going to tell us, because again, usually the registrar is the one or the people that are running the exam. So that's what I would probably do, is you have your 3 hours of time, and then you'll have like 10 minutes of grace at the end after the 3 hours to get your stuff together. So hopefully that answered your question. Yeah. If the registrar kind of abdicates their responsibility for running the exam, then it's all in my power, then I get to decide, and that's probably what I would do. So if I'm running it, yeah, you'll probably get like 10 minutes at the end to scan it or to get everything together and submit it. If the registrar is running it, then I have to follow what the registrar is going to tell me. We're all playing it by ear. Never thought I'd be teaching through a pandemic or plague or not sure what. It's always interesting. Every year is always new challenges always happen. But yeah, we're doing our best. We're trying our best. It did answer it to the best of our ability. Yes. And of course, you get to see exponential growth and all these mathematical models. Everyone's talking about it. You can see basically math is being used all the time in terms of policy making, and all of our government officials who are relying on epidemiologists, the doctors, the statisticians, and the modelers who are working. And again, it's always to the best of our ability. We're working with the best data that we currently have. That's what we'll call Bayesian optimal. That's as best as we, with the current state of knowledge that we have, this is our best decision. And again, you're seeing, even when you see graphs like this, we're getting to the point where we have you're getting kind of these curves. And this curve is, say, like this is time. And this is the number of new cases. Well, everyone's looking at that, and basically we have to integrate this curve. Because this is the number of new cases, and the area under the curve here is the actual, total number of cases or people infected. And again, everyone's trying to flatten out this curve. So you have this total number of people that you have infected. You have a fixed number of people, but say if you had 100,000 that's infected, well, holy crap, that's going to overwhelm the system. So the idea then is to help spread that 100,000 over a longer period of time to help, because again, hospitals are a commodity. They have a certain number of beds that are available, and if they go past that threshold, then at that point they have to start turning people away. But if we can somehow flatten it, we have the same number of people that eventually get infected, but we're able to spread it out over a longer period of time, then again, the hospital won't be overwhelmed. We won't have to turn people away, and hopefully there's a smaller number of deaths, as opposed to basically there's no medical help available for people like that. So we're seeing calculus in terms of integrals being used all the time now, and it's being flashed on television. Calculus is very useful, and in terms of the exponential function, we're seeing it every day now on the news about exponential growth, and we're always worried about it being exponential growth. And we talked about that previously, where we definitely do not want to have exponential growth. What we would rather see is some sort of logistic curve. Something like this with an S. That's the logistic curve. We talked about that previously. And when people start to say, "Oh, we'd like to see, it flattening or whatever," what they're really hoping for, what they're really looking for at this point is they're really hoping for an inflection point. This is where the concavity is changing from going up to going back down. And so this point of inflection is kind of really what everyone is hoping for. We get to that point and the rate starts to decrease. And that's what we're really hoping for. Yeah, so you get to see it in action. It's not like previous years where we were showing everyone and like, oh, they're like, oh yeah, like, this doesn't really apply in real life. We'll never see this. Now we're talking about it all the time. So it's kind of weird and cool all at the same time that we have an application and you see it being used in real life and in policy decision making as well. So again, I wish you all the best for the holiday. Make sure you stay safe, wash your hands. Soap is what helps break down the virus. This is what current research is saying. Keep your distance. All of this helps to help flatten the curve. Okay, I'll see you all on Tuesday, and take care.